in this lecture I shall deal with a very important application of X-rays, namely phase diagram determination using X-ray diffraction. We already know that for an alloy system, a phase diagram or an equilibrium diagram is essentially a plot of temperature versus composition, and this plot is divided into a number of areas in which a particular phase or a phase mixture is going to be stable. Phase diagrams are of great importance in material science, and there are several methods by which phase diagrams can be drawn, namely thermal analysis, microscopic measurements, and X-ray diffraction. X-ray diffraction has an added advantage over the other two methods, because using X-ray diffraction we can not only determine the phase diagrams, but we can also find out the crystal structure and lattice parameter of the phases that are encountered in a phase diagram. Now, in this lecture I will concentrate on phase diagram determination by using X-ray diffraction, and I will consider only a two component or a binary system. Say for example, this is a typical phase diagram of two components A and B. This is a typical phase diagram of two components A and B, where the components are totally miscible in the liquid state, and in the solid state they form a continuous solid solution. In the solid state they form a continuous solid solution. That means, even if the composition change takes place, this continuous solid solution has the same crystal structure from here to here, although the lattice parameter will change as the composition of the continuous solid solution changes. Now, this is the melting point of the component A, and this is the melting point of the component B. Now, if we look at this phase diagram, above this line everything is in the liquid state, and below this line everything is in a solid condition. In between these two lines we have two phases, both the solid and the liquid. Now, the line above which everything is liquid is known as the liquidus line, and the line below which everything is solid is known as the solidus line. There is another typical phase diagram of a two component system here. This is a situation where the two component system is such that two terminal solid solutions form which are alpha and beta near A and near B respectively. The liquidus line is this one and the solidus line is this one. Alpha is a solid, beta is a solid, and this is the field where both alpha and beta solid phases coexist. This is the region where we have both liquid and alpha phase. This is the region where we have both liquid and the beta phase. Now, in order to determine a phase diagram or an equilibrium diagram, we must be able to determine the room temperature equilibria. We must be able to determine the equilibrium phases that exist at room temperature, and side by side we must be able to determine the phases which are present at higher temperatures. And we must remember these 4 points when we deal with a phase diagram. At the temperature of investigation, each alloy must remain in equilibrium. You see, that is the reason why phase diagrams are also known as equilibrium diagrams. Now, if a constant temperature line is drawn across the phase diagram, it must pass through single phase and two phase regions alternately. As you can see here, if you draw a line parallel to the composition axis and perpendicular to the temperature axis, what we find? We find up to here it is a single phase, from here to here along the line it is a two phase, again it is a single phase, again it is a two phase, again it will be a single phase. So, both single and double phases will coexist alternately. So, if a constant temperature line is drawn across the phase diagram, it must pass through single phase and two phase regions alternately. So, while in a single phase region, a change in composition involves a change in lattice parameter. So, if there is a change in the lattice parameter, what will happen in the diffraction pattern of the material? It will reflect, it will be reflected as a shift in the diffraction line positions. So, if we go back to the previous diagram, say for example, this is a continuous solid solution. So, within this single phase region, if we go for different compositions, what will happen? Because of the different compositions, the lattice parameters will be different, because if suppose the B atoms are larger than A atoms, as we move along this axis, the unit cells will contain more and more of B than A, and as a result of which the lattice parameters will be higher and higher, larger and larger. Now, if we take a diffraction pattern of this single phase from different compositions of B, there will be a change in the lattice parameter values, and this will be reflected as a shift in the values of shift in the positions of the diffraction lines. We will see to it very soon. Now, fourthly now, while in a two phase region, a change in composition of the alloy will involve a change in the relative amounts of the two phases. Without any change in their lattice parameters. There is an error here. It will be without any change in their lattice parameters, not compositions. So, this is another important thing to remember, that while in a two-phase region, a change in composition of the alloy will involve a change in the relative amounts of the two phases without any change in their lattice parameters. Now, let us see what it means. If we look at this particular phase diagram, say for example, if we take different alloys made up of this much of B, this much of B, this much of B and this much of B, then what will happen? Say at this particular temperature, here, if what we find that up to this composition, it will be single phase alpha, and at this temperature from here to here, it will be two phases alpha and beta. Composition of alpha will be given by this point at this particular temperature. Composition of beta will be given by this point on the same temperature scale. And when we move from here to here, as the composition changes, more and more B is produced, the lattice parameter of alpha and lattice parameter of beta here do not change. So, what happens within this two phase region? Although the lattice parameters of alpha and beta do not change, and these are fixed by the composition as shown by here and here at that particular temperature, the relative weightages of alpha and beta will change. For example, at this particular temperature, if we are on a higher side of B, then there will be more of beta phase than while we are on the towards the side of A, where will be less of beta, more of alpha. We will come to it soon. So, what is the procedure to be adopted to determine the phase diagram of a two component system at room temperature? So, the first thing is we design a series of alloys. Then make small ingots from these alloys by melting and casting. The third step is homogenize the ingots for a long time at a high temperature in the solid state. This is very, very important. Homogenization for a long time is needed, so that the phases will be in equilibrium. Cool the homogenized ingots very, very slowly to room temperature. Prepare powder specimens by grinding or filing of the ingots, of the homogenized ingots. We re-anneal the powders in order to remove stress, if any. Finally, we examine the powders by X-ray diffraction to find the room temperature equilibrium. So, this is how we find out the room temperature equilibrium by X-ray diffraction process. Now, when we will deal with the phases at higher temperature, what should we do? The first step is make the powder and seal the powder specimens in small evacuated silica tubes. Then heat the tube to the desired temperature. We keep the tubes at a particular temperature till equilibrium is reached. Now, if it so happens that the high temperature phases can be retained by rapid cooling to room temperature, then that is what we do, quench or rapidly cool the specimen at a very rapid rate to room temperature. Are the phases stable? If we find yes, the high temperature phases are stable, Then what we do? Examine the powders by X-ray diffraction at room temperature to find the phase equilibria at that high temperature. On the other hand, if the high temperature phases cannot be retained by rapid cooling from the high temperature, we have to examine the powers by X-ray diffraction using a high temperature camera or a diffractometer, where you can keep the specimen at the desired high temperature for prolonged period of time. Say for example, when we are dealing with this kind of a phase diagram here between two components, where you have liquid at high temperature and a solid below the solidus, which is a continuous solid solution. Continuous solid solution means you can have as much A in B and as much B in A as you want to be without changing the crystal structure. Say for example, we choose these 7 compositions. 1 and 7 are the pure components A and B, and 2, 3, 4, 5, 6, these are 5 different alloys of A and B, 2 containing 28% of B, 3 containing 48% of B, 4 containing 58% of B, the fifth one containing 68% of B, and the sixth one containing 88% of B. Now, at room temperature, when you make specimens from those 7 samples and take the diffraction pattern, say this is the kind of diffraction pattern that we get. This side is 2 theta is equal to 0, that means low theta side. This is 2 theta is equal to 180, that means the high theta side. Now, what we find here, say for example, for the pure component 1 A, this is the diffraction pattern. So, we get diffraction lines for the component A. What will happen to this pattern when we go to the alloy 2? If you remember, the alloy 2 is made up of pure component A with 28% of B, and if the B atoms are larger than A, what will happen to this particular composition? The lattice parameter will be higher than the case of this, although the crystal structure everywhere is the same, but this one will have a higher lattice parameter, this one will have a still higher lattice parameter because more of the large atom B is present, this one will have still larger value of the lattice parameter, this one will have still larger value of lattice parameter, etc., etc. Now, when there is an increase in the value of the lattice parameter, it means there will be an increase in the D values also. So, when we look at the Bragg reflection, lambda is equal to 2D sin theta. Lambda is a fixed quantity because this is the radiation we are using for doing the experiment. So, if D is large, automatically theta will be lower. So, you see that due to the addition of the component B in A, where B atom size is higher than the A atom size, the lattice parameter at the D values of the lines will increase, as a result of which they will shift to lower and lower theta values. They will shift to lower and lower theta values, and this is what we observe in the diffraction patterns. Say this particular pattern is for component A, this particular pattern is for component B, and what we find that although the crystal structures are not different, but you look at the line positions, these lines are present much towards the shorter values of theta, and here the lines are shift towards the higher values of theta. This is bound to happen because B atom size is bigger, B lattice parameter is bigger, B d values are bigger than of A. Automatically these will be shifted more towards lower theta values, and these will be shifted more towards higher theta values. Now, when we go to the sample 2, an alloy, we find that yes, these lines are present in the pattern, because as I told you, the crystal structure does not change when we have a continuous solid solution, but only thing that happens is the lines will be shifted slightly toward the lower theta side, and for that reason for the alloy 3, alloy 4, alloy 5 and alloy 6, there will be a continuous shift of the lines towards lower theta values, and finally this will be the pattern for the component, pure component B. Now, we will deal with what is known as the lever rule. Say for example, when we deal with this two-phase region here, when we deal with the two-phase region here, we have both the phases alpha and beta present. Now, if we take any temperature here, and if the temperature line cuts this two-phase region at P and at Q, say if we are dealing with an alloy of composition R, say, then alpha and beta, these two phases will be in equilibrium in this region, and at this temperature value the composition of alpha will given by this point. So, you can read out the composition from the composition axis. In a similar manner, the composition of the beta phase you can read out from the point Q. So, this will be the composition of the beta phase. Now, these are the composition of alpha, this is the composition of beta. So, what happens when we have an alloy having the composition given by R? So, this alloy will have two phases, alpha having a composition given by this and beta having a composition given by this. But how much will be the weight fraction of alpha in this alloy? That will be given by this length divided by the entire length. So, the weight fraction of the alpha phase at this temperature will be given by this length divided by the entire length. And what will be the weight fraction of the beta phase? It will be this length divided by the entire length. So, we can simply write it down. So, W into R minus P for beta, I am sorry, for alpha is equal to W into Q minus R for beta. So, you see that here the alpha, it is for alpha phase, W alpha R minus P is equal to W beta Q minus R. So, how much will be the weight fraction of alpha by beta, it will be q minus r divided by r minus p. So, it will be q minus r divided by r minus p. So, what will happen if we take an alloy of composition R, then at this particular temperature, say if we draw a line parallel to the composition line, P will be the composition of alpha and Q will be the composition of beta. Within the entire range at this particular temperature, there will be no change in the composition of alpha and no change in the composition of beta. But what about the weight fractions of alpha and beta? They keep on changing as we move along this line, and at this particular temperature we find that the weight fraction of alpha divided by the weight fraction of beta will be equal to q minus r, that means this length, divided by r minus p, that means this length. So, this rule is known as the lever rule, and that will give us an idea of how much of the two phases will be present in an alloy within the two phase region. So, one thing we have to remember, that at any particular temperature when alpha and beta phases are in equilibrium, the composition of alpha and beta will be unchanging. For example, at this temperature composition of alpha will always be given by that and composition of beta will be always be given by that. So, what will happen if you take different compositions of the alloy is that the relative weight fractions of alpha and beta will change only. Now, if suppose we want to find out the room temperature equilibria for this kind of a system. So, what we do as before, we take a sample for the pure A, a sample for pure B, and we choose several samples in between and make X-ray diffraction specimens out of H in the usual manner. And then when we examine the diffraction patterns, what we find, you see, this is for the pure component A, sample number 1, and these are the diffraction lines for the pure component B. You see, one thing we have to remember in this connection, that a particular phase, whether an element or a compound, will give rise to a particular diffraction pattern, and a particular diffraction pattern, what we mean by that? That diffraction lines at specific values of theta and relative intensities of a specific type. So, when we talk about a diffraction pattern, we talk about both the positions of the lines corresponding to the theta values as well as the relative intensities of the lines. So, an X-ray diffraction pattern of any element or compound, that means for any particular phase, is unique, just as the fingerprint of individuals is unique. By examining the fingerprints of two different persons, you can identify them as different persons. In a similar way, just by examining the X-ray diffraction pattern, when I call X-ray diffraction pattern, two things must be kept in mind: the positions of the lines as well as the relative intensities. So, when we talk about an X-ray diffraction pattern, it is unique for a particular phase, an element or a compound. So, this is the way by which we recognize one phase from another. So, if we look at the diffraction pattern taken from the component A, this is given by 1, and diffraction pattern taken from the component B, which is 7 over here. Then as we move, what happens in this place? Say for example, when we move from this composition to this and this, we are in the alpha phase, and if we assume that beta atoms are larger than the alpha phase, since the weight percent of beta is increasing, we will have here and here the alpha phase is the same phase, but the lattice parameters will be larger, or the d values will be larger. That means the lines will be shifting towards lower theta, as we have already seen. So you will see that when we are alloying with B for the phase alpha, how these lines are shifting to lower theta, and this goes on till the alloy 3. Then what happens when we take, say, alloy 4 and 5? What will happen? You will have lines for both alpha and beta present simultaneously in the diffraction pattern, and as we can see here, the alloy 5 has a higher amount of B compared to the alloy 4. So naturally, the diffraction pattern of alloy 5 will show stronger lines of beta, and this one will show weaker lines of beta, because in this case, in the alpha beta mixture, amount of beta will be much higher than over here. So the beta lines will be much stronger here than over here, and this is what we see here. Say in case of 4, again the dark lines are for the alpha, you see, and these weak lines are for beta. So as we go to alloy number 5, what we find, the amount of beta increases in alloy 5 from alloy 4, as a result of which the beta lines are much stronger here. And what about the alpha? Alpha lines are much weaker in this particular case. So you see that when we reach the alloy number 6, practically alpha has fully vanished. So we will have only the beta lines. So these are only the beta lines for alloy number 6. Now if we go back to the phase diagram, what we will find, 6 to 7, as we go from alloy 6 to alloy 7, then the beta will be more enriched in the B component. So what will happen? The lattice parameter or the d values will shift to shorter theta values, and that is exactly what happens here. You see, it is, this is beta and this is the B component, and you see the lattice parameter shifts to the theta, lower theta values. So in this way, at any particular temperature, say at room temperature, we can figure out where the whole thing changes from alpha to alpha plus beta to beta. And if it so happens that we can have equilibrium at higher temperatures also, and if by quenching from the higher temperature the phases can be preserved, then by doing extra diffraction at room temperature also, we can figure out what the phase distribution is going to be like. Now if we go back to this diagram, we observe there are two important lines in the phase diagram. This is this and this. These are known as the solvus curves or solvus lines. Just as this line over here is known as the liquidus, this line over here is known as the solidus, these two lines are known as the solvus lines. And there are two methods, X-ray diffraction methods, by which we can determine the location of the solvus lines as a function of temperature. So, the locations of the solvus curves as a function of temperature can be easily done using the X-ray diffraction method. Now, let us see how the whole thing is done. There are two XRD methods for determining the solvus curves, and these are: number one, disappearing phase method, and the second method is the parametric method. So, there are two different X-ray diffraction methods to determine the solvus curves in a phase diagram. These are: number one, the disappearing phase method and the parametric method. Now, we will describe both these methods separately. Say for example, we make a number of alloys having the compositions shown over here. Say 1, 2, 3, 4, 5, 6, 7, 8 alloys we make having different weight percentage of B. Now, using the disappearing phase method and the parametric method, it is possible to find out the points where alpha changes into alpha plus beta, and therefore, once these points or these compositions are marked, we can have a smooth line through them, and that will give us the solvus line. Similarly, we can find out the solvus line on this side also. You see, the way it is done is very simple. Say for example, if we consider, say, a temperature given by this. So, if we make an alloy over here of this composition, okay, if we have an alloy of this composition at this temperature, it will be the alpha phase totally. If on the other hand, we take an alloy of this composition on the other side here, it will be the alpha and beta phases both. Now, when you take a composition given by this point at this temperature, it will have alpha and beta both, but here the amount of beta will be much less compared to the amount of alpha. Now, if I make an alloy, farther down the percentage weight percent of beta, a less beta, say we have an alloy of this composition. So, when we take the diffraction pattern at this temperature from the sample, again I will find lines of alpha and beta, and at this case the beta lines will be much weaker because the amount of beta in the sample is much less. A time will come when, say, if we come to this point, this position, if we make an alloy of this particular composition, then the beta lines will be so weak that those lines will not be visible in the diffraction pattern at all. That means the beta lines will disappear from the pattern. So, in the disappearing phase method, what we do? We take a series of compositions. Say if we want to find out the solvus point at the temperature T, we make a large number of alloys, and then say for example, we have an alloy over here, find out the X-ray diffraction pattern. It will give you alpha lines as well as beta lines, but if I move down this line and make an alloy with less weight percent of B, then also I will get the alpha lines and the beta lines. But what will happen to the beta lines here? Corresponding to the previous case, beta lines will become little weaker, because in this point for an alloy of this composition, the amount of beta will be much less than, say for example, of this composition. So, as we are going down towards the A composition, the amount of beta in the alloy will become less and less, and then a time will come when we have an alloy of say this particular composition, which will show lines of alpha only, no beta lines will be there, they will be almost disappearing. So, that is the point which will be lying on this solvus curve at this particular temperature. And if we follow the same method for each and every temperature, for several temperatures, it is possible to find out by joining these points the solvus curve. Similarly you can do by taking a large number of alloys on this side and getting their XRD patterns and figuring out when the alpha phase completely disappears, and those points can be joined by a simple curve to show the solvus line. So, this is all about the disappearing phase method. But you see, sometimes we have a problem. Say for example, if we are dealing with two components, one has a very high atomic number, the other has a very low atomic number, then what will happen? Say A is a very high atomic number element and B is a very low atomic number element. You see, higher atomic number will mean higher value of small f, the atomic scattering factor, and small capital F, the crystal structure factor. For a higher atomic number, for a higher atomic number element, both small f, the atomic scattering factor, and big F, the crystal structure factor, will be large. And for a smaller atomic number element, both small f, the atomic scattering factor, and capital F, the crystal structure factor, those will be smaller. As a result of which, the diffraction lines from A will be much stronger compared to the diffraction lines of coming from B. So, the beta phase will have much weaker diffraction lines compared to the alpha phase. So, it may so happen that when the beta phase is present in very small amount, but the corresponding diffraction pattern may show no beta lines at all, because beta has got much lower value of small f, the atomic scattering factor, and big F, the crystal structure factor. So, you see that this is a source of error. That means, say for example, even when beta is present to the extent of 5 weight percent, but since the beta phase produces a much weaker diffraction pattern, those lines may not be visible with respect to the alpha lines in the pattern. So, although the beta amount is present to an extent of say 5 or 10%, we may miss that. So, this is a source of error in the disappearing phase method, when the components have widely different values of crystal structure factor F, that means widely different value of the atomic number. Now, we come to the second method, the parametric method. So, what we do in the parametric method? You see, if we look at if we look at any temperature T over here, and if we look at here, we have got the alpha phase. So, if we look at the the diffraction pattern or the of A and find out the lattice parameter, and if we go to an alloy of A and B here, we are still in the alpha phase, and if B atoms are bigger than the A atoms, what will happen? We will be still in the same phase, but the lattice parameter will be more. So, a time will come as we go from this place to this place and make a number of alloys, we will see that the lattice parameter will be different. As we are adding more and more weight percent of B in the alloys, the lattice parameter will increase. So, we will have a situation that as we are adding weight percent of B, this is the lattice parameter of the alpha phase. So, they are increasing. Again, if we go back to this diagram and if we take alloys on this side, it will be alpha and beta. But remember, at this temperature, alpha lattice parameter is fixed given by this, beta lattice parameter is fixed given by this at this temperature. So, if we make a number of alloys and measure the lattice parameter of alpha for each and every one of those alloys and plot them and extrapolate them. So, what we find that we will have a situation, it will be a line, straight line, because all the lattice parameters are the same, and you can extrapolate this line and extrapolate this line, they will meet, they will intersect at this point, and the weight percent of B given by the point Z is the corresponding point on the solvus curve. So, this is what is known as the parametric method, and here also there may be a problem. If it so happens that A and B atoms are of almost similar size, then what will happen? The change of lattice parameter of alpha will be minimal. So, in that case we have to find out the solvus point by the intersection of two very similar and flat curves. This is perfectly flat, and here if the B atoms or A atoms are not much different in size, then the increase in the lattice parameter value of alpha will be minimal. So, in that case this line, instead of having this position, it will be a much flatter line, and you see when we find out the point of intersection of two flatter lines, it is very difficult to pinpoint where they have intersected. So, you see that in such cases parametric method may not be very useful, and we must find out other methods to determine the phase diagram. For example, the microscopic method will be a good method to do so. Now, there are complicated phase diagrams. I will just give you one example. So, here we have got the alpha and beta terminal solid solutions, and we also have a compound which has got extended solid solubility. If it are a pure compound, if gamma were a pure compound, in the phase diagram it should have been a single line, but the very fact that it is extended over an area, that means it shows that gamma has much wider solid solubility. Otherwise, this diagram is not much different from the phase diagram which I have shown you before.